Okay, looks like we're ready. So,
Yep.
welcome everyone to the virtual Allen School, Paul G. Allen School Colloquium, School Computer Science Engineering Colloquium. Add this here in the call. If I butchered this name, I'm in trouble. So, welcome to our virtual colloquium. It's really a pleasure to have Jihao Jia today, giving us a talk on his work in machine learning systems, making sure that all these crazy models that are machine learning engineers, right, actually run well and do what they're supposed to do. Just as a quick reminder here, please everyone stay on mute, but if you could enable your webcams, that would be great because seeing human faces is something that I think is super useful in this moment. You know, we want to see faces moving, seeing all your dogs and pets. So please turn on the cameras if you can. Remember that we taking asking questions via the chat. I'm monitoring the chat and raise your hand there, and then I will make sure that we get you how to notice that at the right time. Okay.
Yep.
All right. With that, Jihao, please take it away. It's really great to have you virtually here. So,
Yep. Thank you so much, Luis, for the kind introduction. Hi, I'm Jihao. Welcome to my talk. And today I'm very excited to present my work on automated discovery of machine learning optimizations. And I would like to start this talk by motivating the necessity to accelerate machine learning computation. This figure shows the largest ML training tasks over the years. And the red line indicates that the amount of computation in largest machine learning training doubles every 3.4 months, and therefore it is critical to accelerate machine learning computation. And the machine learning model, especially recent deep neural network model, can be described by a computation graph. Each node in the computation graph denotes a tensor algebra operator, such as convolution or matrix multiplication, and each edge indicates the input or output tensor for each operator. You can simply think of a tensor as an n-dimensional array. And machine learning systems are one of the key ingredients in machine learning. They perform the computations defined in a machine learning model onto today's distributed heterogeneous hardware backends. And the bottom figure shows a representative hardware architecture for Summit, which is now the #1 supercomputer today. It includes a number of compute nodes connected by a high-performance network, and each compute node has heterogeneous processors, such as CPUs, GPUs, and also heterogeneous memories. And I want to list three main challenges of building machine learning systems and motivating why it is hard and non-trivial to build efficient machine learning systems. The first challenge is the massively parallel nature of machine learning, because tensor algebra can be parallelized in many dimensions, and it is critical to select the best combination of these parallelizable dimensions to achieve efficient parallelization performance. And the second challenge is the introduction of new machine learning operators. Today's machine learning systems are not trying to optimize a fixed set of operators. There are new ML operators introduced into current ML systems on a regular basis, and it is important to be able to support optimizations for these newly introduced operators. And the third challenge comes from the hardware side. In order to achieve efficient resource utilization on today's heterogeneous hardware, it is necessary to effectively manage different processor kinds and complex memory hierarchy. And as you may have noticed that the challenges come from both the machine learning model side and the heterogeneous hardware sides. And all three challenges are mostly specific to machine learning applications, but haven't been widely considered in conventional compiler or runtime systems research. And the combination of these challenges makes it difficult to build efficient ML systems. And current ML systems, including TensorFlow, PyTorch, and many other systems, they rely on manually designed performance optimizations and greatly apply these optimizations to improve the runtime performance. As a more concrete example, consider here we are trying to optimize the input computation graph. And the blue box shows the search space of functionally equivalent computation graph. And our task here is to find an optimized solution in the search space. And in current ML systems, we apply a sequence of manually designed graph optimization to obtain an optimized computation graph. And in addition to use this manually designed optimization to do graph level optimizations, the same idea has been used to optimize many other tasks in machine learning deployments, including how we parallelize the computation across multiple devices, where should we place data in the deep memory hierarchy, and what should be the data layout for each intermediate data. So all these tasks are currently optimized using manually designed optimizations. So what's the problems here? What's going wrong with manually designed optimizations? I want to list two main limitations of today's manually designed ML optimizations. First, it is just very hard to design, especially for distributed heterogeneous hardware backends. And the current design heavily rely on human heuristics and ad hoc methods. And the second limitation is suboptimal performance. Although currently we spend tons of efforts trying to manually design potential performance optimizations for machine learning computation, this only gives us suboptimal performance. And we have observed a potential performance improvement of more than 10 times even in production ML systems. And my research enables a new way to build machine learning systems. Instead of relying on manually designed optimizations, my research focuses on automated discovery of machine learning optimizations. And there are two phases in the method I developed. The first phase is automatic generation of possible optimizations. Instead of using manually designed optimizations, I built systems that can automatically generate optimizations, which covers today's manually designed ones and also discover many additional ones that are previously missing. And by using these more optimizations, we are able to reach out to more programs in the search space that were invisible before. And the second phase is the efficient search for high-performance programs. I built efficient search algorithms that leverage the topology of the search space and can quickly discover highly optimized solutions in the search space. And by using this methodology, I have built three major systems throughout my PhD. Starting from a machine learning model, I built Tassel that can automatically discover computation graph optimization and return highly optimized computation graph. And in order to parallelize the computation defined in the graph across multiple devices, I built FlexFlow that can automatically discover efficient parallelization strategies. And finally, for the execution on each individual device, I built Lux that can automate data layout and placement optimizations. And in this talk, I will first present Tassel and then move on to FlexFlow. And I also want to list three main contributions of my PhD research. The first contribution is better runtime performance. I built systems that accelerate machine learning training and inference by up to 10 times compared to current ML systems. Second, it requires much less amount of engineering effort to achieve these performance improvements. This is because the code for discovering these optimizations is up to 38 times less than manual implementation of these optimizations. And the third benefit is fast deployment. Our systems only require a few minutes of automated search to discover highly optimized programs. And this system has been widely used by many industry companies and national labs to accelerate machine learning computations in production. And I will first present Tassel that can automatically discover computation graph optimizations. And before I dive into Tassel, let's first look at how current ML systems optimize computation graph. Current ML systems use rule-based optimizer that includes a list of manually designed rules. One such example is that if we have a convolution followed by a ReLU, we can fuse it to a convolution plus ReLU operator. In current systems, we can greedily apply these manually designed rules on the input graph whenever possible to obtain an optimized computation graph. And each rule is implemented in source code, and the right figure shows the TensorFlow code for fusing convolution plus ReLU. Overall, TensorFlow currently involves around 200 different rules implemented in 53,000 lines of code. So as you can see that currently people have spent lots of efforts trying to manually design these rules, but it has three fundamental limitations. First is robustness, because these rules are designed based on human heuristics on common models and hardwares. These heuristics do not apply to all model and hardware combinations. And as a result, we can find people on GitHub or Stack Overflow complaining that if I use TensorFlow's rule-based optimizer, sometimes the performance is even slower than without enabling these optimizations. And the second limitation is scalability, because as we have seen before, these new operators and graph structures are continuously introduced into current systems. However, optimizing a new operator using existing rule-based approach is very expensive. As a data point, TensorFlow currently involves around 4,000 lines of code to optimize convolution, and you may imagine a similar amount of code efforts to optimize every single new operator. And the third limitation is performance, because human heuristics may miss some optimizations for specific model and hardware combinations. And let me show you a concrete motivating example based on ResNet. The left figure shows the optimized graph of ResNet using existing rule-based approach. I think many of you may have heard of ResNet. It is an extremely commonly used model for image classification, and people have spent tons of efforts trying to manually optimize the computation graph of ResNet. But it turns out that we still miss some optimizations. And here is how it works. So first, we can change this 1x1 convolution on the left to a 3x3 convolution on the right. So this 1x1 and 3x3 are the kernel size of convolution. A larger kernel size means you have to do more computation, but you can always mimic the behavior of a smaller kernel using a larger kernel size by just setting the extra parameters to be 0. And you may wonder why you have to do that, because this step will introduce additional computations and decrease the runtime performance. You may wonder why I have to decrease the performance in order to do graph optimizations. And here's the reason. Because once you have two convolutions with the exact same kernel size, now you can fuse it to a single convolution kernel. And this is an optimization because originally you have to launch two separate convolution kernels and access the input tensor twice. While in the new graph, you only have to launch a single convolution kernel and access the input tensor once. And additionally, you can also fuse the convolution and the following addition to a single convolution operator by changing the weights of the convolution operator so that mathematically you still compute the exact same thing. And finally, you can fuse the convolution and ReLU as we did before. And the very interesting result of this example is that the final graph is 30% faster on B100 GPU, which is a more recent generation of GPU, but 10% slower on K80 GPU, which is an older generation of GPU. Even if we run both graphs on GPUs, but if we use different generation of GPU, it shows different performance trade-offs. And note that we cannot simply add this as an additional rule in our rule-based approach, because it only improves performance for specific model and hardware combinations. So any questions about this example?
Well, so I have a question. Could you contrast a little bit how, maybe you're going to get to that later, how this compares with approaches taken by, say, TensorRT or TVM and so on?
All right, right. Yes, actually, I will explain that in the later once I have presented Tasso. And maybe we can answer that question after the presentation of Tasso. Thank you for asking. Great. So hopefully this example shows the high complexity of designing graph optimization for deep learning, because it depends on the graph optimization depends on the machine learning operators we use, depends on the graph architectures we have, and also depends on hardware backend we would like to run the model on. And different combination of these three components makes it infeasible to manually design graph optimizations for all cases. So what can we do? How should we address this problem? In order to address this challenge, I built Tasso, the tensor algebra superoptimizer. The key idea of Tasso is to replace today's manually designed graph optimizations with automated generation and verification of graph substitutions for tensor algebra. And this replacement has two advantages. First is much less engineering efforts. Instead of writing 53,000 lines of code for manual graph optimizations in TensorFlow, in Tasso's approach, you only need to write 1.4 thousand lines of code to specify these optimizations. And the second advantage is much better runtime performance. Tasso can outperform existing optimizers by up to 3 times by automatically discovering novel graph optimizations, such as the one I have showed you before. So let me first formally define what is a graph substitution. A graph substitution describes mathematical equivalence between a pair of computation graphs. This example shows that if we run convolution on the same input but different weights, that is equivalent to first concatenating the weights, do the convolution, and finally splitting the outputs. And these two computation graphs are mathematically equivalent for arbitrary inputs. So the research question is, how can we automatically discover such graph substitutions? In order to do that, this figure shows the Tasso workflow. We start from operator specifications that describes the set of available operators supported by the hardware backend, and as well as their mathematical definition. And Tasso uses a substitution generator to generate candidate substitutions, which are sent to a substitution verifier to verify the correctness of the substitutions. And finally, all verified substitutions can be used for graph optimizations. And in order to optimize an arbitrary input computation graph, Tassel considers how to apply this verified substitution on the input computation graph. And this gives us a search space of potential computation graphs that are functionally equivalent to the input graph, but have very different runtime performance. And Tassel used a search-based graph optimizer to explore the search space and return highly optimized computation graph based on a hardware-specific cost model. But there are two key challenges we must address in order to use this approach. First, how can we automatically generate these potential substitutions? Second, how can we verify the correctness of these substitutions? In order to do it, Tassel used a graph fingerprints to generate substitutions and use operator specifications plus a theorem prover to verify their correctness. And I'll explain the meaning of these terms in the next few slides. Great. So first, our first job is try to generate these substitutions. Our input here is operators that are supported by the hardware backends. And by using these operators, Tassel first enumerate all possible graphs up to a fixed size by using these available operators as basic building blocks. So in our evaluation, we consider all graphs with up to 4 operators, and the graph substitution generator can enumerate around 66 million different computation graphs. And remember that one substitution is a pair of equivalent computation graph. So a straightforward approach is to directly evaluating all pairs and figure out whether they are equivalent. But this direct evaluation requires a quadratic number of comparisons and won't be able to scale. So one key technique used in Tassel is called graph fingerprinting. The idea is simple. We can first generate some randomized input and run all computation graphs using the same randomized input. And the output of each computation graph becomes its fingerprints. And these fingerprints give us a very nice property, which is if 2 computation graphs give us different fingerprints, they cannot be equivalent because they disagree on the same input. And as a result, we are only interested in pairs of graphs with identical fingerprints. And each such pair becomes a candidate substitution. And in our evaluation, Tassel generates more than 28,000 substitutions by enumerating graphs with up to 4 operators. And we have also applied a sequence of pruning techniques to eliminate redundant substitutions. And after pruning, 743 substitutions remain. And the details of the pruning techniques are available in the paper. And remember that each candidate substitution is generated using some randomized input. So their equivalence on randomized input doesn't mean they are correct for arbitrary inputs. And in order to prove and verify the correctness, Tassel used a graph substitution verifier, which also takes a second input, which is a list of operator specifications that describes the mathematical property of different machine learning operators. One example is that convolution is distributive or concatenation. And the second example is that convolution is bilinear to both input and weights. And each mathematical property is described in first-order logic in Tassel. To describe the distributivity of convolution over concatenation, we have for arbitrary x, W1 and W2, if we run convolution over the concatenation of weights, that is equivalent to distribute convolution into the concatenation. And in order to verify the correctness of a candidate substitution, we ask whether the 2 computation graphs are mathematically equivalent for arbitrary inputs. And we can send this query along with our list of operator specifications to an automated theorem prover. If the theorem prover returns yes, meaning that it can prove the correctness of this query using given list of operator specifications. If the theorem prover can prove the query, then we know this substitution is correct for arbitrary inputs. And this table lists all 43 operator properties used in our evaluation. And the right column indicates the corresponding mathematical properties associated with each first-order axiom. And overall, Tassel generates around all 743 substitutions in around 5 minutes and can verify them against 43 operator properties in around 10 minutes. And a very interesting result of this is that although all candidate substitutions are generated using just one randomized input, but it turns out that all of them are correct for arbitrary inputs and can be verified by our automated theorem prover. And in terms of the effort to optimize supporting optimizations for new operators, in Tasso's approach, our experience shows that it only requires a few hours of human effort to specify its properties. We think it's more efficient than writing thousands lines of code for manual optimizations. And again, our approach requires much less amount of code. Any question about the generation and verification?
Yeah, Zihao, there's a question here in the audience. Magda, would you like, you can unmute yourself and ask the question. Yeah.
Great, thank you. Yes, I have a clarifying question. So in Tasso, you generate these kind of random graphs and then prune them and then verify them using the logical rewrite rules specified by the user. Why not take those rewrite rules, the mathematical equivalence expressions, those as input, and use those to generate kind of equivalent graphs that you know will be correct and therefore kind of opportunities for exploration?
Right. That's a great question. You're right that if we start from these 43 operator properties at the beginning, we can reverse and the step and generate all substitutions. But the problem is how to come up with this list at the beginning, because at the beginning, so we don't know which properties are more will be useful for proving this for proving the correctness of different substitutions. So, and the generation of this list is actually guided by the generator. So the generator will give us what are the substitutions that have passed this random test, and the generator will think these are highly likely to be correct. And we use this generator as input and try to figure out what are the fundamental mathematical property that will lead to the correctness of different substitutions. So,
hold on, so just to clarify, so what did the user specify? In the previous slide, you had the user specify some rules. Right, those weren't those user specified?
Right. And actually, all the rules in this figure are user specified. So the rules on this table are more fundamental mathematical properties. So the associativity, distributivity, and the operators substitutions. The graph substitutions we are trying to prove, for example, in this figure, is more complex graph rewrites. So in order to prove this, you need to use a sequence of multiple fundamental mathematical property in order to prove that this is correct.
Great, thank you.
Thank you for asking.
Yeah, I have a quick follow-up question. Are you confident that the trends for models are going to still lead to graphs with tractable search spaces? So you're assuming, so the amount of work you have to do here is proportional to the complexity of the graph, right? So which is a function of the models. And is this likely to continue being tractable as models get more complex?
Yeah, that's a great question. So our experience shows that it is still currently we think it's still tractable, because for each new operators you only have to define a small number of new rules, and but you're right that this number of rules you have to describe may grow exponentially or more as we add more operators. But
yeah, especially with dynamic graphs, like dynamic graphs and these new types of much more complex models, right?
Right. Yeah, we agree that will be a research challenge. But we think our approach is at least more efficient than manually define, because for manually define you have to manually design and implement every single substitutions. And we think this way of that number of substitutions will grow. It also grows exponentially. And we think our way of generating and verifying substitutions is more efficient than manually design and implement every single substitution.
Great, thank you.
Yes.
Sorry, I have a question. Does the theorem prover prove the substitutions theoretically or experimentally, like using input and expected output?
Oh, I'm sorry, I didn't hear the question. Sorry.
Does the theorem prover prove the theorems theoretically or using input and expected output, like experimentally?
All right. So the theorem prover will prove the correctness theoretically. So it takes this list of operator specific properties as axioms and try to use these axioms to prove every single substitution, every single candidate substitution. But this is proved mathematically.
Just one more last question on this before we move on. So Alton, you had a question about scalability. Please feel free to unmute and ask the question. Yeah.
Okay, so I have a question about the scalability of the random graph generation. So you say that you can generate all these substitutions in 5 minutes, but this is for the 4 operators in the graph. So like if I add one more operator, is it going to take a lot longer?
Oh, you're right that our approach for the generator, the number of candidates, the number of possible graphs grows exponentially as you consider larger graphs, right? And this is actually a limitation with our current implementation, because in our current approach, we have to save the fingerprints on a single machine, on the DRAM of a single machine. And in order to do that, we can only enumerate for graphs with up to 4 operators. But this is not a fundamental limitation of our approach. And we are currently working on building a distributed generator. And by leveraging the distributed DRAM memory to save our fingerprints, we are able to go to much larger substitutions. Thank you for asking.
I see. Thanks.
Okay, actually, there's one final one here in the chat. Let me just ask, and then we need to let Zhihao continue. The question was, why generate? This is from Marisa. So he asked, why generate lots of graphs, but not a single big one, and then use fingerprints to discover semantically equivalent nodes in the graph? Would that enable reuse?
Yep. That's a great question. And I think, so the approach he described is feasible. And so our consideration is to guarantee completeness. Because for enumerating all possible graphs up to a fixed size, we can guarantee that we didn't miss any substitutions, within our size limitations. So for all substitutions within, with up to 4 operators, we can always discover all of them. So our design is to guarantee completeness in our approach. Thank you for asking.
Great, thank you. All right, so keep going, please.
Great. So far I've presented how to generate and verify these graph substitutions. And our goal is to use this verified substitution to improve computation graph. And in order to do that, Tasso used a search-based graph optimizer that explores the search space and return highly optimized computation graph. And one of the key components in the search of the graph optimizer is a cost model for evaluating the performance of different candidates' computation graphs. And the cost model is based on individual operators' cost, and we can measure the cost of each individual operator directly on the hardware backend. And I will talk about the details of the cost model in the second half of the talk. And the search-based graph optimizer uses cost-based backtracking search algorithm to explore the search space. This is because we need to get rid of local optimal solutions. Because in our previous example, sometimes in order to do optimization, you need to decrease your performance at some intermediate step. So that's why we use a backtracking search algorithm to escape from local optimal solutions. And in our experience, optimizing a machine learning model from scratch takes less than 10 minutes. And we think it's efficient because before you deploy your model for inference and services, you only have to run this search algorithm once. And so far, I've presented the overall design and workflow of Tasso. Let's look at some end-to-end performance evaluation. This figure compares Tasso with the existing rule-based optimizers, including TensorFlow, TensorFlow XLA, and TensorRT. And Tasso can achieve competitive performance on standard models by only using automatically generated substitutions. This means that Tasso is able to discover all performance-critical optimizations for standard models. And the more interesting results are for these new emerging models, for which Tasso can achieve more significant speedups. And you may wonder why you have such significant speedups on these new models. And we have digged into the details of these new models, and we found that they have new operators or new graph structures that haven't been fully optimized in existing rule-based approach. So there are missing rules. But because Tasso can automatically discovering possible optimizations for new operators, that's why we can achieve a significant speedup. And to briefly recap, Tasso enables automated discovery of graph optimization. And the first phase is generating the search space by using automated generation and verification of graph substitutions. And the second phase is searching for high-performance programs using a cost-based backtracking search algorithm to get rid of local optimal solutions. And there are also some prior work on automating machine learning optimizations, including TVM and tensor comprehension. So these systems focus on optimizing as individual operators, while Tasso addresses a different problem of automating graph-level optimizations. And we're also planning to combine the techniques in Tasso and TVM to jointly optimize machine learning deployments. And methodologically, this prior work automating machine learning optimizations by relying on a manually predefined search space. But for a graph optimization problem, it is infeasible to manually define a search space of equivalent computation graphs. And Tasso addresses this challenge by automatically generating the search space. And Tasso is also the first deep neural network graph optimizer that can automatically generate substitutions, leading to much less engineering effort, better runtime performance, and also stronger correctness guarantee. Tasso is fully open source and has been used by many companies to accelerate machine learning computations. So any questions about Tasso?
So I have a question.
Yes, there's a question. Yeah, Magda. Yeah.
Yes, thank you. So I have a question. So what is the benefit of this design compared to the traditional cost-based optimizers that kind of can be found in relational database systems?
I think one challenge here is that there are new operators introduced into current ML systems on a regular basis. So the challenge is how do you design and implement the optimizations for this newly introduced operator. So in traditional approach, we can have engineers to manually design and implement these optimizations or these rules, but it takes a long time. It takes several months or even up to years to add optimizations for newly introduced operators, right? And Tasso addressed this problem in a different way. So in order to support optimization for new operators, you only have to tell Tasso the mathematical property of these new operators. And Tasso can automatically generate and verify possible graph optimizations related to this new operator. I think so Tasso enables a more efficient way to enable graph level optimizations for tensor algebra and to deal with the evolving workload and computation of machine learning.
I see, thank you. So we can try to discuss at the end, but it seems that kind of in a relational system, you also specify logical rewrite rules that kind of logically specify potential optimizations around a new operator, and then the system can kind of apply these rewrite rules to generate graphs and prune the graphs, and there's typically an efficient algorithm for how to apply rules and how to traverse them. But maybe that's a longer discussion question that we can take at the end.
Yep. And yeah. I guess actually a main difference between machine learning workload and database workload is that the quick evolvement of machine learning computation, because people keep adding new operators. For example, for convolution, there are more than 20 variants of convolution for different types of tasks. And the implement system challenge is how do you support optimization for many variants of convolution. So whether should you manually design and implement every single one of them, or can you use a more automated and systematic way to design, to generate and verify these optimizations? And we can also talk offline or at the end of the talk. Thank you.
Jihao, there's one more quick question. Then after Remy, we should let Jihao proceed. So Remy, please feel free to ask the question.
Yeah, so my question is that you have two phases. First phase, you discover equivalent rewrites, and then second phase, you run this search algorithm to see how you can apply these transformations. Yes. So I think it's fair that compared to the long training time, 10 minutes is not a lot. But do you see a way to somehow learn some heuristics about how to apply these transformations from every time you run the search algorithm? Like every time you run it, the system becomes smarter.
Right. Yes. So it's a very good suggestion. So we are currently considering some learning-based approach, so that instead of searching for highly optimized solutions, we can learn some heuristics about how to apply this graph level optimizations. And we are currently working on a project that tries to use graph neural networks to accelerate the search and to learn some heuristics. That's a very good suggestion. Thank you.
Yeah, thank you. That's very exciting.
All right. Please keep moving. Yeah.
Great. Yeah, so far I have presented Tasso that can automatically discover highly optimized computation graph. And in order to run the parallelize the computation graph across multiple devices, next I will present FlexFlow that can automatically discover efficient parallelization strategies. And before FlexFlow, people are using data and model parallelism to parallelize training. The bottom figure shows data parallelism. In order to train a machine learning model on a training data set, in data parallelism, we can partition the training data set into multiple batches and train different batch along with the entire model on different GPU devices. And alternatively, in model parallelism, instead of partitioning the training data set, we can partition the computation graph of your machine learning model and train different subgraph along with the entire data set on different GPU devices. So data and model parallelism are the default parallelization strategies used in current ML systems, including TensorFlow, PyTorch, and many others. So they are very simple to design and implement, but only give us suboptimal performance. And there are also some manual design strategies that try to combine data and model parallelism to accelerate specific machine learning models. But the design of this strategy generally takes many weeks, and the design strategy only work for specific machine learning models, but cannot generalize to other models. And recently, Google built a system called Colloq-RL that tried to use reinforcement learning to optimize model parallelism in tens of hours. But the performance of this system is fundamentally limited by the performance of model parallelism. And FlexFlow enables automated discovery of fast parallelization strategies. The key idea of FlexFlow is to search over a significantly larger space of possible parallelization strategies beyond data and model parallelism. And FlexFlow has two key advantages over previous work. First is much faster deployment. FlexFlow only requires a few minutes of automated search rather than weeks of manual design or tens of hours of reinforcement learning. And it also achieves better runtime performance. We can outperform existing machine learning systems by up to 10 times by automatically discovering more efficient parallelization strategies. And FlexFlow considers a four-dimensional search space of possible parallelization strategies. We call it the SOAP search space. It includes the sample, operator, attribute, and the parameter dimensions to parallelize training. And let me explain the meaning of these four dimensions. First, the sample dimension considers partitioning training samples across devices. And this dimension has been used in data parallelism to parallelize training. The bottom figure shows parallelizing a 1D convolution using the sample dimension. The computation of 1D convolution can be parallelized in 3 dimensions. So we use a cube to describe its computation. So it has a sample dimension for computations related to different training samples. It has a parameter dimension for computation related to different training model parameters. And there is also a third attribute dimension. And I'll explain the meaning of attributes in the next slides. By using the sample dimension, we end up assigning different training samples to different GPU devices. And the second dimension considered in the SOAP search space is called the operator dimension that considers partitioning machine learning operators across devices. And this dimension has been used in model parallelism. The idea is that we can assign the entire computation of different operators on different devices and use different devices to parallelize training. And the third dimension is called the attribute dimension, which considers partitioning attributes within a training sample. And you can think of attributes as pixels. When we are training some high-resolution image, we can partition the image into multiple sub-images and train different sub-image on different GPU devices. And finally, the parameter dimension considers partitioning model parameters within an operator across multiple devices. We can divide the parameters within an operator into multiple subsets and compute different subsets on different GPU devices. The advantage of this approach, this dimension, is that we can eliminate data transfer for parameter synchronization because each parameter is only computed on a single GPU device. And in addition to consider individual SOAP dimensions, in our design, we also consider hybrid parallelism in the SOAP search space. And the right 2 figure shows 2 hybrid parallelism examples that try to use multiple SOAP dimensions to parallelize training. And in our design, it is guaranteed that different strategies will perform the exact same computation, and therefore we can get the same model accuracy by design. And the advantage of this guarantee is that when we are trying to find efficient parallelization strategies in the SOAP search space, we don't have to worry about model accuracy loss and can focus on improving the runtime performance. And let me show you a concrete visualization example. So the top figure shows data parallelism for Google's inception model. So each box indicates the computation for one operator. We have 2 dimensions here. We have a horizontal parameter dimension and a vertical sample dimension. And different color means assign the corresponding computation to different GPU devices. And in data parallelism, we always end up assigning different training samples to different GPU devices. And the bottom figure shows one possible strategies among many others in the SOAP search space. It is 1.2 times faster than data parallelism. In the bottom strategy, we can use data parallelism for some layers, use model parallelism for some other layers. We can use hybrid parallelism for intermediate layers. And we can also use different degree of parallelism for different layers. So all these parallelizable dimensions and flexibilities are considered in the SOAP search space. SOAP defines a very comprehensive search space of possible parallelization strategies. But in order to discover efficient strategies in the search space, there are two key challenges we must address. First, SOAP contains millions or contains billions or even more possible strategies, and it is infeasible to enumerate every single strategy in the SOAP search space. And second, evaluating one strategy directly on the hardware backend is very slow because it requires measuring distributed executions on up to hundreds of GPU devices, and may take several minutes to just measuring one strategy. And in order to address these two challenges, FlexFlow uses MCMC, Markov Chain Monte Carlo search algorithm to explore the search space, and we use a novel execution simulator to accurately estimate the performance of different parallelization strategies. And this figure shows the overview of FlexFlow. We take two inputs. One is the computation graph that describes the computation in your machine learning model. And the second input is the hardware topology graph that describes the set of available devices we would like to use for training and the interconnection between these devices. And FlexFlow first uses the MCMC search algorithm to generate candidate strategies. Instead of directly measuring the strategy on the hardware, we use an execution simulator to simulate the execution of this strategy and return the simulated performance back to the search algorithm. This feedback will be used for generating future candidates. And once this search procedure is completed, the best discovered strategy will be sent to the FlexFlow distributed runtime for parallelizing training using the best discovered strategy. And our design of the execution simulator is based on two key observations of machine learning computation. First, the performance of machine learning operators is highly predictable. And this is because most machine learning operators are based on dense linear algebra, and their execution time on current accelerators, such as GPUs, is very reliable and predictable. The second observation is that although some machine learning models may have hundreds or even up to thousands of operators, but most of the operators are the same, and each model only involves a very, very small number of distinct operators. And by using these two key observations of machine learning computation, we build an execution simulator that first measures each distinct operator and the communication bandwidth on the actual hardware devices once, and use these measurements to simulate the parallelization execution of different strategies. And our execution simulator achieves very fast simulation. It is 3 orders of magnitude faster than real executions. And the simulator also achieves very high accuracy. The relative difference between simulated and real runtime performance is always within 30% in our evaluation. And more importantly, the simulated performance preserves real execution time ordering, meaning that if one strategy has better simulated execution time, it also has better real execution time. And this makes the execution simulator a very efficient cost model for exploring the SOAP search space. And this figure compares FlexFlow with existing manually designed parallelization strategies. The main takeaway of this figure is that FlexFlow can find faster and more scalable strategies, even compared to the ones that are manually designed by domain experts. And in addition to this model, we have also evaluated FlexFlow on up to 6 real deep neural networks and observed up to 3.3 times speedup over the best existing strategies. And for the impact of FlexFlow, it is currently being used by Facebook to train production models, and FlexFlow can increase training throughput by up to 10 times. And FlexFlow is also used by Los Alamos National Lab to train machine learning models for precision medicine, and can reduce training time from days to only a few hours. FlexFlow is also used by researchers at Stanford University to improve the accuracy, scalability, and the performance of graph neural network. So graph neural network is a new class of neural network trying to learn on graph structure data. And in this talk, I will briefly describe our current collaboration with Facebook. And this figure shows the deep learning recommendation model from Facebook. It is a core production model for ads recommendation. So whenever we browse any Facebook websites, all the ads shown on the websites are recommended by this model. So you can tell that this is a very important model for Facebook to make money. However, this model is very hard to train in a distributed way, since it involves a mixture of compute and communication-intensive workloads. And this figure shows a simplified version of the model, and each box in the figure actually indicates a subneural network. And this figure shows the training throughput of this model using data or model parallelism. The x-axis indicates using different number of GPUs, and the y-axis indicates the training throughput achieved by using that number of GPUs. As you can see that by using data and model parallelism, we cannot scale to more GPU devices, since increasing the number of GPUs doesn't improve the overall training throughput. And this is also why before FlexFlow, Facebook is mainly using CPU machines to train this model. And this is the training throughput achieved by FlexFlow. By automatically discovering more efficient parallelization strategies, FlexFlow can improve the training throughput by up to 10 times compared to data and model parallelism. To recap, FlexFlow enables automated discovery of fast parallelization strategy. The first phase is defining the SOAP search space by exploiting the massively parallel nature of tensor algebra and consider different dimensions to parallelize machine learning training. And the second phase is MCMC search algorithm plus a novel execution simulator to explore the search space and discover fast parallelization strategies in a few minutes. So any question about FlexFlow?
I have a quick question. This is it's really awesome and impressive. Are the cost models static or?
All right. So the cost model is static. So this is a static optimization. So we. Yeah. So we
see. So then, go ahead.
Oh, go ahead.
Sorry. Go ahead.
Right.
Well, if it's static, I'm just curious, like, how would you address, say, there's some strategies that might be better than others depending on the loads on a cluster, right? So if the interconnection network is busy, then your communication cost changes, and even your own execution, if you have people, you get what I mean, right? Some cost models just fundamentally can't be static, so.
Right, I agree. Right, so FlexFlow is designed for static case, so that it assumes that you have the exclusive access to these clusters, and we try to leverage this observation of machine learning. The computation is very predictable, and all data transfers are large communications. So we leverage this fact to design the cost model, and we also think about how to apply this idea to dynamic workloads. So one idea is that we can statically generate different optimizations for different types of dynamic workloads. Say, given a specific, utilization of the clusters, we can generate different parallelization strategies. And I think it's also an open problem to us of how to dynamically, how to extend the workload to dynamic models. In which case you don't have a static model at the beginning. How can you optimize parallelization for given dynamic models? And we are currently working on that. That's a great question.
Great. Thank you. So you have 10 minutes to wrap up, by the way. So
great. Yeah. So far I've presented Tasso and FlexFlow, and in addition to these two projects, I've also worked on 3 other systems throughout my PhD. First, ROC is a system for large-scale graph neural network. It enables training of large graph neural network models not supported in current ML systems. And by using these large models not supported before, we are able to improve state-of-the-art model accuracy on well-known datasets. And second, LUX is a system for fast graph analytics on multiple GPUs. It uses 2 novel execution models to enable critical GPU optimizations and achieve up to 20 times speedup over existing distributed graph analytic systems. And third, Isometry is a system for efficient data transfers in heterogeneous clusters. It uses a novel path planning algorithm to find optimal path for data transfers in heterogeneous clusters and achieve up to 5 times faster data transfers. And so far, I have presented the work I did throughout my PhD, and I also want to use a few minutes to briefly describe my future research agenda. And my long-term research goal is to make real-world machine learning applications extremely easy to program and fast to run. And with that, I want to talk about three aspects of my future research plan, ranging from systems to machine learning. First, how should we enable future system optimizations for machine learning? Second, how should we design future machine learning system interface? And third, how should we better support future machine learning applications? And before I talk about future system optimizations for machine learning, let's first look at how current ML systems optimize computation. In current ML systems, we perform a sequence of optimizations and optimize different tasks in a sequential ordering. And this approach makes it easy for us to design and implement different optimizations because we can focus on optimizing one task at a time. But this also means joint optimization opportunities. And our previous work have discovered that if we jointly optimize graph and data layouts, just two example tasks in the whole deployment stack, if we jointly optimize the two tasks, it is 1.3 times faster than optimizing the two tasks sequentially. And this really demonstrates the high potential of joint optimization opportunities. And therefore, I believe future machine learning systems should be able to perform end-to-end system optimizations and can jointly optimize different tasks in the machine learning deployment stack. And second, I also plan to work on redesigning future machine learning system interface. The left figure shows current ML system interface. Currently, we rely on users to specify a machine learning model and provide system optimizations for a given machine learning model. And the right figure shows a future machine learning system interface I would like to build. Instead of requiring user to specify machine learning models, we can allow user to describe the constraints and the requirements for specific machine learning deployment tasks. For example, a user can tell us what's the minimum accuracy the user would like to achieve for given data sets, what's the maximum latency the user can tolerate for inference services. The user can also describe memory constraints and memory energy and many other constraints. And by taking these constraints as input, the future ML systems should be able to perform automated search of models and system optimizations and can return programs that satisfies user-provided constraints. And third, I also want to work on systems to better support future machine learning applications. Current ML systems focus on optimizing and supporting static and dense ML models, including convolutional neural networks, recurrent neural networks, and transformers. But this only covers a very small fraction of machine learning applications that are interesting in machine learning community. And recently, there's an emerging trend to explore dynamic and sparse ML models. And there are many ongoing research projects along both directions. But so far, we don't have efficient system support for dynamic and sparse models. And my recent work on graph neural network is just one step towards both directions. And in the future, I want to continue my investment and building systems to better support future dynamic and sparse machine learning computations. So all of my PhD work are open sourced, and there are more information online. And I also want to use this opportunity to thank my advisor and collaborators, without whom none of the project I presented would be possible. And with that, I want to conclude the talk, and I'm happy to take any additional questions. Thank you so much.
All right, thank you. Oh, we have a few more minutes for questions. I know we asked a bunch along the way. So anyone, just type it in your chat, raise your hand in chat here, and then I'll moderate. So. All right, Tensuchu, please go ahead.
Yes, I actually have two questions.
Yes.
So in the first part of the talk, you rely on a theorem prover. So the user specifies the identities that the new operators have to are supposed to satisfy, and then you generate randomly those substitutions. But then the theorem prover needs to prove that they are equivalent, because otherwise you are not able to exploit these. So my first question is, how powerful, what kind of theorem prover do you use? And if you have any comments on the dependency on the theorem prover. And my second question is about, maybe I misunderstood this, but you mentioned that you also improve the accuracy of your models.
Yes.
And if you improve the accuracy, my understanding is that you're actually changing the precise semantics of the linear algebra expression, or I should say the mathematical expression that you're optimizing. And I wonder where is the border between which optimizations are preserve the semantics and which optimizations do not preserve the semantics but improve the accuracy.
Right, right. So probably maybe I can answer the second question first, since we're on the right slide. So actually we preserve the exact same computation, and the reason why we can improve accuracy is because we are able to support large scale models. In current ML systems, if you want to use train graph neural network, you have to make sure that all the intermediate tensors must fit on a single GPU device. But we break that restrictions and build a distributed systems for large-scale graph neural networks. And as a result, we are able to train significantly deeper and larger models that cannot be trained before. And we found that by using these significantly deeper and larger models, it can actually achieve better accuracy on today's commonly used data set. And this is actually not super surprising, because if we look at what happened in convolutional neural networks or language models, people have been saying that using deeper and larger models can actually achieve better accuracy. Yeah, and so go back to your first question. So what theorem improvers we use? So actually we use Z3 as our theorem improver. So our input to the theorem improver is some axioms. So we treat these machine learning operators as opaque functions, and we define the mathematical properties for different machine learning operators. And we ask the theorem improver to prove that whether a given substitution is correct or not. And we didn't use any advanced feature of theorem improver. And we think if we should also be able to use other theorem improvers.
All right, so we have one final question from Remy, and then we'll thank Jihao again.
So my question is related to Dan's theorem improver question. So you showed us a list of axioms you use. Are there any non-identities in the list? I didn't read quite carefully. So I remember most of, this is a list. Most of them in the form are like just simple identities. Do you have anything that depends on, theory of integers or something like that?
Yeah, so there are some non-identity. I'm trying to figure out one. So the answer is yes. So there are some properties that are not identity, but I'm trying to figure out. I'm trying to look for where they are. Sorry, I think so if you look, I'm not sure if you can see my mouse. This is one example. So we can replace a convolution. We can replace the average pooling with a convolution. So this is not identity, because convolution and pooling are two separate operators. But if you do average pooling, we can replace it with a convolution by carefully setting the weights of the convolution.
All right, so thank you. So Raz has so how can we say no to Raz? Raz, you have the last question.
Thank you. So you have nicely automated the creation of optimization given the set of operators. So the next step seems to be to ask the question, how sensitive is the power of the optimizations to what operators I give you? Clearly, some new operators will be created just because we have new models, but there are some operators that have nothing to do with the functions in the network. Can you comment on the sensitivity to that, or what insights human need to provide to the creation of operators?
Right. So I think yes. So for new operators, our approach is I think it's more efficient because we can generate new optimizations for new operators. But I mean, additional benefit is that we can also support new hardware backends. Say that whenever we need to support optimization for a new hardware devices that we haven't seen before, we cannot directly reuse existing optimizations designed for current hardware backends, because the new hardware may have very different architecture and performance trade-offs. And so our approach can automatically searching for how should we apply these optimizations that can achieve good performance for a given new hardware backends. I think these are two advantages of our approach.
Thank you.
Thank you for asking.
All right. Thank you again. Thank you, Jihao. All right, everyone. Enjoy the rest of your day. Bye.
Bye-bye.